And now we're getting to algorithms. I'm going to present a certain type of algorithms, which I like to call simultaneous computation with oracles. We've actually used oracle-based games, which are related to algorithms, probably in our childhoods. And these are defined by having a protocol that provides limited information in which the player needs to find an algorithm to determine the solution based on some decisions on what question to ask next of that oracle based on information from a previous one. For example, Battleship, right? All you get to say is a location, and all you hear back is hit or miss. You don't find out how close you were, only hit or miss, and you don't know what type of ship you've hit if you've hit it. Mastermind is sort of the canonical one because you're actually trying to guess a secret code, and you're given information on how many of the colors are correct and how many both are correct in color and in position. And then, of course, 20 questions. 20 questions has been around for generations. And it's just a set of yes or no questions. The one person thinks of an object, and the guesser tries to guess it in 20 yes or no questions. So these aren't just games. They're actually used extensively in computer science in cryptography and security because systems tend to leak very specific kinds of information. I mean, even in a system that's secured, when you try a password, you're told it's incorrect. That's information. And so computer scientists use oracles to try to figure out what's the most you can do with that limited information. What happens if you're able to read a message that's sent to, for example, the bank from an ATM? Could you then later send an identical message, even if you didn't know what the contents were? If you sent an identical message later, would that mess up things? So those are the sorts of useful reasons for having an oracle. So an oracle is any computerized system that you can interact with and get information out of. And we try to make algorithms to figure out what we can do with that information so that then we can turn around and make the security higher so that it leaks less or different information. Okay. And now this is a really good fit for quantum because in quantum, likewise, in all calculations, we can't get full information. We can't find out the full quantum state. And so we want to figure out what operations we can do and short of measurement or measurement, but the question is, what can we do if we can't get full information? Because that's going to be the reality in a quantum system. Oracle-based quantum algorithms start with an oracle in the middle. And this oracle, you can ask it a question, so you give it some set of information, and it gives you an answer back with some set of information. And so the algorithm itself is all of the stuff you do with that information. What should I ask it, and what should I do based on the answer it gives? All right, so we want to put gates before and after the use of the oracle, and the oracle is going to provide that piece of information. Now, I do want to note that at this moment, we're not going to do useful algorithms. We're learning algorithms to try to get an intuition into the nature of quantum algorithms and how it is that quantum computers can get speed over classical computers in some cases. So I'm going to describe an oracle. So we're going to do two algorithms. I'm going to describe an oracle and then design the sequential and then the simultaneous algorithm based on that oracle. And the idea is that a classical computer would be forced to do a sequential algorithm. But with quantum properties, we can do a simultaneous algorithm that goes faster. But again, only in these limited circumstances. Okay? So you can think of these as proofs of concepts of what quantum calculations might be able to do. So let's do one. It's based on the Bernstein-Vazirani algorithm. And so I'll call it the Bern-Vaz oracle. So there exists this 3-bit secret code, and you want to figure out what that is. And so this oracle contains a sequence of CNOT gates in which each input corresponds to a 1 in the secret code and the control for the response, which is the target. So this means that inside this oracle, there are some CNOT gates, but maybe not connected to everything. So in this case, the secret code we're going to work with is 0, 1, 1. And so I've made these two a little bit darker to indicate these are the two that have a CNOT gate that are connected to the response. Okay. All right, so let me show you how this works. Let's imagine I give a guess of 1, 0, 1. So these two have CNOT gates, and there's only one. We recall that if you have a white bulb as the control to a CNOT gate, nothing changes. And so there's a single black ball connected to a C naught, so then the response is going to flip one time. Now, a second guess is 0, 0, 1. Notice that the only thing I changed was the ball that wasn't connected to a C naught at all. So that means my output will be the same. It'll toggle one time based on this black ball that's going in here. Okay. Now, if we give it 1, 1, 1, we can see that there are 2 black balls connected to C naughts as control, which means we'll flip this input twice, which will get us back out the black again. Okay. So that's how the oracle itself works. And now we need to figure out how to build something around it that will allow us to figure out what that secret code is. All right, so note that this does not directly tell us the secret code. We did 3 probes, and we can find out some information from that probe, right? We can figure out that this top is a 0 because when we toggled just that 1, nothing happened to the output. So that's one piece of information we got. But we didn't necessarily figure out how many, whether these were 1s and 0s on the output. So here, with this probe, 0, 0, 1, we actually did figure out that the third bit is a 1 because it's the only black ball going in and it caused a flip. So by the end of this, we've figured out that this is a 0 and this is a 1, and we don't know the middle one yet. And then on the third probe, we already know the first one doesn't matter. We already know that the last one is a 1. And so by giving a black for the middle one, we actually figure out that this is a 1. So with these 3 probes, just how they happen to be constructed, which is chance, I was not doing it for this reason, we actually could figure out all 3 bits. But there's a more methodical approach we can use to figure out the 3 bits. Okay, so I invite you to think about a methodical approach. No matter how many bits we have, we could have a 5-bit input, a 10-bit input, right? However long this secret code is. What is the sequence of probes you should do and get out one piece of information each time, right? Which is whether that black ball stayed black or turned to white. What would we give as the sequence of probes? And how many would it take? And I will wait just a second. I invite you to pause the video right now and think about that and try to come up with something yourself. And then I'll go through it here. All right, so the sequential algorithm is to do a series of probes where you only ever have one black ball, because then that tells you whether that black ball is attached to a C naught or not. So if the response does not flip, like this first case, that means it's a 0. But in the second case, it does flip, which means the second one is a 1. And then in the third case, it also flips, which means the third one is a 1. So we're guaranteed that if I have an n-bit code, I can figure out the code in n trials. All right, so let's look at what we can do with quantum. All right, so we're going to input all white balls for the guess and a black ball for the response. And we're going to put H gates before and after the query to the oracle. Okay? And we're going to expose phase flip so that instead of having only a single piece of information that might change, which is the response, we're actually going to cause the other bits to change, which allows us to have more information. Okay, so we know that, and by the way, this is a very common way to do an algorithm, is to put everything through a series of H gates at the beginning, and then put them through a series of H gates at the end to get back pure states, and then see what you've got. So we've got these H gates. Now we're in the situation that for these C naughts, if there's a C naught, we've got a positive 50-50 going in as control and a negative 50-50 as response. And we already know that if that happens, if the response is a negative 50-50, it causes the control to change sign, and ultimately when it goes through an H gate, change from white to black. But it doesn't change the response. So no matter how many C naughts are connected to this negative 50-50 response, it will stay the same. And perform that phase flip on every single one of those inputs, that's a positive 50-50. So let's see what happens here. We had a 0, 1, 1. And so now the two ones got a negative sign. And so then when we put everything through an H gate, we actually get the exact secret code, 0, 1, 1. And so in a single operation with this oracle, because we preceded and succeeded it with H gates, we actually end up finding out the secret code in a single trial. So this is what I call simultaneous computation, in that because it compels everything to 50-50, it stores all possible combinations, but then the nature of the operations is such that when we take it out of superposition, it puts it into what we want.